Thanks, Ken. Our plan for today is to guide you through how medium voltage electrification is transforming industrial decarbonization, enabling cleaner and more efficient operations. Decarbonization is driving real change, especially within the industrial sector. Multiple global initiatives like the Paris Climate Agreement and COP28 emphasize the need to cut emissions and transition to renewables. Manufacturers are facing new mandates, new fines, and taxes aimed at reducing carbon footprints and cutting nitrous and sulfur oxide emissions. The energy transition is accelerating and pushing companies to adopt cleaner processes, remain profitable, and address rising material and energy costs, as well as increasing equipment lead times. To solve these challenges, the energy transition will require different and novel approaches. There are 6 major decarbonization pathways that are shaping this transition towards achieving nearly 37 gigatons of CO2 mitigation by 2050. There is a particular focus on the top 4 avenues, which account for 80% of this strategy. Those are, noted here in green, wind and solar energy plus renewable fuels, energy conservation, electrification of process heat, and adoption of hydrogen as a fuel. Electrification, especially as the grid decarbonizes rapidly, is among the most promising strategies for lowering industrial emissions, improving efficiency, and reducing NOx and SOx. We'll now cover some of the challenges that manufacturers are facing, starting with the top left: strict decarbonization mandates, penalties, and taxes, maintaining profitability in energy-intensive sectors, rate of change, or the need to stay competitive and agile due to changing consumer demand for greener products, rising global raw material costs, longer equipment and component delivery lead times, and finally, surging costs of natural gas energy. These factors make electrification and process heat innovation both critical and urgent for our industry. Electric process heating is critical to our pursuit of net zero and helps build a global climate strategy. On the left side here, you see several different strategies that could be pursued towards net zero. The one that we're going to focus on today is the one in orange, where we talk about electrification of process heating, electrification of spare heating and hydrogen production, and also development of electrified processes. We'll now highlight some of the major advantages of process heat. Using cleaner electricity reduces ownership costs. Electric heaters offer nearly 100% efficiency. And as the grids decarbonize, emissions from electric heat fall dramatically. Finally, renewable fuel production increasingly depends on cleaner process heat, making electrification a centerpiece for any effective climate strategy. I'll now talk about some of the historical applications for electric heaters and fired heaters in the oil and gas industry. On the left side, as far as electric goes, some of the common applications are glycol reboilers, gas instrument and fuel gas heaters, seawater and lube oil heaters. You'll note a picture of an electrically heated 12 megawatt two-phase column reboiler on the left side. As for the gas-fired solutions, feed and product exchangers, dehydrators, LNG vaporizers, and FCC heaters. And of note, here is a picture of a steam source horizontal reboiler. For over 75 years, electric process heaters have been used in oil and gas, but mostly at lower power ratings, typically under 250 kilowatts. Now we see heater packages scaling up from 5 megawatts to 200 megawatts, with more industrial processes transitioning to electric heat over the past 3 years. This evolution enables scalable, reliable, and safer process heat for the modern industry. I'll now make the transition to focus more on medium voltage heaters, specifically Watlow's POWERSAFE medium voltage integrated heater and control system. We like to say that this is your pathway for scalable, reliable, and safer process heat. How are industrial heating solutions evolving? The current fired solution is typically gas-fired and emits greenhouse gases. The low voltage electric solution requires step-down transformers, high amperage panels, and lots of cabling, as shown in the graphic just above. For the medium voltage electric solution, we're able to eliminate those step-down transformers, use low amperage panels, and require significantly fewer and smaller cables. Medium voltage integration dramatically simplifies installations and improves efficiency for multi-megawatt heating applications. So what exactly is medium voltage? It's defined as greater than 1 kilovolt and less than 100 kilovolts per ANSI C84.1. And some of the common utility medium voltage levels include 4.16, 12.47, and 13.8 kilovolts. This matters because higher voltage means lower current for the same power, thus reducing cable sizes, switchgear costs, and resistive losses. This is essential for powering large heaters without massive low voltage cabling penalties. The table on the right demonstrates the significance of moving from a 690 volt low voltage solution to a 4160 volt or 6900 volt medium voltage solution. You will note up to 90% reduction in the number of branch circuits or cables required when comparing a 690 volt low voltage solution to a 6900 volt medium voltage solution. I'll next talk about some of the key considerations for designing medium voltage electric heaters. To start, electric arc discharge and safety mitigation is critically important when designing medium voltage heaters, as safety is our priority. Electrical field strength for analysis for safe, reliable operation, partial discharge risk mitigation, and reliability and durability, which covers both power switching and heating element design. For heating elements, we need to make sure that the insulating material must be thick enough to prevent any unwanted electric discharge, yet be thin enough to provide the best possible energy transfer. In other words, balancing insulation thickness for safety versus heat transfer efficiency. A second consideration is managing terminal enclosure temperatures to enhance product life and durability. On the right side here, I'll cover some common errors to consider, which are simply oversizing low voltage element designs that can result in high internal temperatures and rapid durability loss. Successful medium voltage heater designs require robust safety and engineering and domain expertise. The recently introduced IOGP S723 standard now provides guidance for these medium voltage thermal systems, which was previously lacking in the industry. So what is POWERSAFE? As it says on the slide here, POWERSAFE is a medium voltage electric thermal solution that offers longer heater life and reduces the downtime associated with fossil fueled equipment by fully integrating a safe and reliable electric heat exchanger and control system with unique design to lower coil temperatures. Some of the POWERSAFE features include heater lengths up to 20 feet for design optimization, fewer vessels and consolidated heat exchangers for streamlined installations, demonstrated element reliability up to 7200 volts, optional 10% element redundancy to minimize bundle replacements, heating element technology that is based on proven low voltage elements used in over 100,000 installations, electric field analyzed elements for safe and reliable operation, 100% UL 1030 and partial discharge inspection of individual elements and entire bundles. And finally, double epoxy sealing to ensure electrical insulation remains robust, even in humid environments. The last slide I'll talk about is the medium voltage heat exchanger bundle architecture. Our system offers the best-in-class spare element isolation and connections, as shown in the top two pictures that demonstrate how a spare element will look as shipped, and then how that spare element becomes an active element if it requires any service. We also have a novel busing system design that eliminates lead wires entirely. This matters because in traditional medium voltage systems, lead wires are prone to partial discharge or small electrical breakdowns that degrade insulation and can eventually cause failure. By removing this risk, POWERSAFE improves long-term reliability. Our system also offers permanent seals for water vapor ingress protection. We're the only system on the market that eliminates a need for bakeout, even after extended storage. This is a time saver both during commissioning and maintenance cycles. Watlow also uses a small diameter heating element which operates at a lower coil temperature compared to larger elements. This helps extend the life of the system and improves efficiency. OptiMax heat transfer technology improves thermal performance and reduces the pressure drop across the heater. Some of the benefits that customers can expect are reduced maintenance downtime and thus maximizing operational uptime, enhanced reliability through moisture management mitigation during manufacturing to achieve consistent product performance, and finally, safety improvements that enable remote and unmanned operations. I will next turn the presentation over to Eric Ludwig to discuss the medium voltage controller.
All right, thank you, Nick. I appreciate that. We're now going to transition over to the medium voltage controller and how it works and how we can accelerate the electrification process due to some of the technology that exists in the marketplace today. As many of you know, medium voltage soft starters have been used in the market since the 1970s, so they have over 50 years of experience with the use of those types of starters to start motor loads in the industry. These particular soft starters use solid-state thyristor power switching in their circuits in order to start that motor efficiently. I've got a diagram over here on the right-hand side that goes through and depicts exactly how a motor starter, soft starter works. You see this center thyristor stack. These are back-to-back thyristors that regulate the voltage over to the motor during the soft starting process. By using these known building blocks of the soft starters, we can manipulate that and transition that into an industrial heater controller within the system. These soft starters typically will vary the voltage within the system as they're starting the motor. A resistive heating element is very similar to that, other than it's not a motor. Obviously, it is just an electrical heater. So as we vary that voltage to the resistor, we can vary the power to the resistor and thus manipulate exactly how much power the overall application will see. By using that technology, we can then accelerate exactly how we bring the controller to market. Watlow has partnered with a very reputable medium voltage thyristor SCR supplier with over 40 years of experience doing this. This brings reliable and proven technology to the market. We'll transition now to exactly how this works. So a resistive heating element is, just like it says, a resistive heating element. The power that goes into it is basically just a combination of voltage and current. And as you vary that voltage, you can vary the output of the system. So the technology is really based on Ohm's law, where, as many of you know, V equals IR, or the current going through the system, is a combination of the voltage and the resistance of the heating element. Obviously, within a resistive heating element, though, you are trying to manipulate the power over a period of time. Within that period of time, you want a constant power output or vary by the duty cycle that you need to produce the power. Therefore, it's not just a soft starter type system. It's really a system where you are trying to provide power on a continuous basis. So in the motor soft starters, you have this bypass contactor up here in the upper part of the diagram. You no longer need that within a control system for a medium voltage heater. We can eliminate that particular contactor and just use the soft starting technology of the thyristor in order to power the unit. So the output power that you get from the heater itself out here would be the voltage, and whatever voltage you're giving that, times the current, times the square root of 3. You get 100% efficient power conversion from the electrical power that's given that to the thermal power into the system. So by varying the voltage, we can also then vary the duty cycle or the power output to the unit using the same technology as the soft starters within the business. So the diagram down here just shows you how that works. You've got these reverse parallel thyristors with a gate control on them. By firing that gate at a certain position within the sinusoidal wave, we can turn on and off those sinusoidal waves at any frequency that we would like to. And by doing so, we can vary that voltage or the effective voltage that gets out to the heater itself. So let's dive into that just a little bit deeper. There are a couple different types of control that you can do with a heating element. You can do what's called contactor control. That's basically on and off technology. If the contactor is on, you're getting 100% duty cycle out to that heater. So 100% of your voltage gets applied to the heater and 100% power is on. You can't really change that. It's either all on or it's all off with a contactor. With an SCR or thyristor, you can basically manipulate that voltage, how often it turns on, how often it turns off within a period of time, effectively creating a duty cycle between 0 and 100% during that base time period. Watlow uses a zero-cross burst firing technology within its system to ensure that we are providing adequate voltage with less harmonics and also keeping the element temperature of the heater constant over time. We do this, like I said, by using the zero-cross burst fire technology. There's a diagram in the lower side of the presentation slide here that shows you this. So if you're using a DCS and you're providing a 0 to 100% duty cycle into our system and telling us you want, say, 25% power, we would gate fire the SCRs at a 25% ratio and thus get the graph here in the middle part of the screen, the 25%. You'll see that it doesn't go on for 25% of the first couple cycles of the wave and then turn off like you would see in some of the traditional pulse width modulated systems. Rather, we burst fire this, and by burst firing, mean we're turning on and off the waves throughout the period so that you level the load throughout that period. If the total time period were the length of this graph right here, you're basically getting 4 bursts within that 25% duty cycle. This ensures that you're spaced apart enough to keep the element temperatures as constant as possible while still only giving 25% of the wattage output into the system. That's very important for the longevity of the heater. The more constant we can keep that element temperature, the longer life you're going to get out of that particular heater. If you want to adjust the power levels, then you just adjust the duty cycle associated with how much power you want to input into the system. So if you want to jump to a 75% duty cycle and get 75% of the power output of that heater, you set your duty cycle to 75%. Typically, you can do that through a 4 to 20 milliamp type input signal. We convert that to a 75% firing rate through the SCRs and thyristors right here. And then you get an output pattern similar to this one that I'm showing right here. The burst fire, again, spreads that out so that you're firing along the entire period of the system here. And the zero cross technology ensures that you're only switching this at the zero cross of the sinusoidal wave. Again, reducing any harmonics that you would build into the system and ensuring a nice, smooth power wave into the heater itself. The thermal response time of the systems are typically fairly long. So you're heating a particular application here. You apply power to that. That power needs to be converted into heat. That heat then heats up the application media, whatever that may be. And therefore, that response time typically occurs over a couple of seconds. You could get faster, you could get slower, depending on your flow rates or whether you're in a boiler application. These base time periods can be changed within the systems, so you can react faster, or if you don't need to react faster, then you can set those higher and react slower. Overall, the POWERSAFE control panels are configured in a very flexible and configurable type of solution. We have these node systems right here, which can be set as either a contactor or an SCR thyristor cabinet. They can be stacked together if you have a larger system with a single feeder or incomer that brings in the power and distributes that power via a busbar system throughout the entire cabinets here. If you get into a complex, very large system, we can also pull the low voltage controls out of these particular cabinets and place them into a separate low voltage control cabinet. This allows some major flexibility to your system. If you have a small system with a single heater and you just need a single cabinet, we can combine the low voltage and medium voltage into a single cabinet without the necessity to have an incomer and or the separate low voltage control panel. That allows you a single cabinet with a single heater to control that particular heater as needed. For larger systems where you have to stack up multiple cabinets to get the total overall power or the number of circuits needed to control that particular heater, we do offer the multiple arrangement of cabinets here so you can stack those up as needed. So as I stated, the system can be built using a combination of these incomers, SCR thyristor cabinets, contactor cabinets, low voltage control cabinets. It can be a standalone unit, or if you've got a larger system, they can be stacked together and used as a bundle within groups. Our voltages do range from 4160 up to 7200 on this, and you can have up to 1200 amps per group. If you need larger than that, we can do multiple groups of cabinets that are set up, so you can get up to 2400, 3600, whatever the case may be for the size of system that you have. Each cabinet has integral earthing disconnects associated with it, fusing, protective contactors, and Watlow's proven temperature limit controllers to ensure that the thermocouples that are embedded inside of these heaters are fed back to the system and any over temperature condition is taken care of adequately. Cable entries into these cabinets can either be through the top side or the bottom side. Same thing with the exits out to the load. You can do that top side or bottom side as well. We do have an HMI that is standard on our systems. If you have a low voltage cabinet within the system, it'll be contained on the low voltage cabinet itself. Otherwise, if you have a single medium voltage cabinet, it'll be existing up here in the low voltage compartment of the medium voltage cabinet itself. So we can combine that low voltage and medium voltage together, put an HMI on the system, and have a self-contained unit. There are hardwired signals that go back and forth to the DCS, as well as communication like Modbus TCP that goes back to the DCS as well for status of everything that is happening within the cabinet itself. Very configurable I/O for any types of commands or statuses you might have for the cabinet itself. And you can do open and or closed loop control, meaning if you have a DCS that wants to operate the system and just give us a duty cycle, we translate that duty cycle into the firing circuit of the heater circuits. We can accommodate that. If you'd like this cabinet to take on the closed loop control, bring a process signal into the particular cabinet, we closed loop control that, control the entire heater sequence based on that closed loop control. The cabinets are capable of doing that as well. Let's talk a little bit about the certifications on the panel. Obviously, safety is a big concern when it comes to medium voltage panels, and you want to ensure that the system as a whole is very safe for any operating conditions that you have. From a system level certification, for North America, UL 347C is the standard for medium voltage solid state resistive load controllers up to 15 kilovolts. This would cover the systems that we're talking about and is a complete system standard, meaning it goes through the enclosure, the wiring, the switching devices, the protection schemes. It covers the entire system to ensure the system is reliable and safe within the application. Same thing with the rest of the world. Outside of North America, IEC 62271-200 is the high voltage switchgear and control gear for AC metal enclosed switchgear and control gear rated for voltages 1 kV to 52 kV. Again, our systems would fall under that particular standard for the rest of the world. These are important primarily because a systems type certification is better than just a power controller type certification. If the only thing certified in your cabinet is the actual switching device itself, the entire system hasn't been evaluated for safety with medium voltage. These two particular standards are the standards that take care of those systems certifications and are the standards that Watlow has chosen to use in order to certify their equipment. They do include type testing to ensure all of the particular aspects for safety have gone through a third-party witnessed inspection to ensure adequate operation of the unit. Whether that's short circuit, arc flash, EMC, dielectric, heat rise type testing, all of this has been completed for both the North American units and the IEC units throughout the globe. So again, a total overall certification of the system to ensure that the third-party safety aspects have been taken care of. In addition to that, we do build in certain protection functions within the system itself. We have arc flash protection, over and under voltage protections, over and under current protections, zero sequence ground faults, SCR over temperatures when you have an SCR within the system, and the aforementioned heater over temperature where we're monitoring those thermocouples and we'll shut down the system if we see any anomalies that are happening. There are several other protection systems built in. Obviously, we have the fusing and the circuit breakers that are part of the overall protection systems, but these are some of the other monitoring type systems we have in the unit to ensure that the system will operate safely. So next, I want to just transition to an example of a system. I know this is a rather busy diagram, so I apologize for the small print in here, but it's really about showing off the major building blocks of the system here. What we have here is a two-group 6 megawatt panels. So you have group 1 up here that has an incomer and 2 SCRs, and group 2 here that also has an incomer and 2 SCRs. These are feeding 4 heaters, which are depicted down here. These are the heater enclosures that are within the system. This particular system has redundancy built in, which is why they chose to go with 2 separate groups of cabinets and 2 separate groups of heaters. It also has redundancy built into the low voltage control panel. So there's a standalone low voltage control panel for this particular system that talks to and integrates with the first group of panels and the second group of panels through the I/O. This is hardwired I/O and Modbus communications to each one of those. The low voltage panel then talks to the DCS within the system to ensure that it's getting the proper signals, not only the duty cycle signals, but status signals, command signals, things like that, that will operate the overall system. We do have separate connections as well. If the customer has a SIS or some kind of safety system that they want to directly interface with the panels. This allows shutdowns for e-stops, shutdowns for other means that do not need to go through the DCS as necessary. We also have power that goes into each one of these. So a single power line coming into the incomer that has a vacuum circuit breaker associated with it. The power is then distributed amongst the panels, and then the output power here goes over to each one of the heater enclosures for powering each one of the heaters. So again, a fully integrated system, lots of flexibility, and a lot of ability to configure it the way you need to ensure that we're meeting your particular application. Next, we'll transition into a few of the case studies that have been done with Watlow and a few of our customers to ensure that the value proposition of the medium voltage package is sustained. The first one has to do with a hot oil systems upgrade out in Singapore. As all of you know, the carbon tax increases that people are seeing are rising very, very fast. In Singapore, you see the charts over here to the right-hand side. They are tripling, quadrupling as we speak. The case for change was pretty obviously based on this. You avoid that massive increase in the taxes and you reduce the overall emissions of the system if you can substitute any of those carbon producing type applications with a electric type application that will perform the same function. In this particular case, it was renewable diesel fuel production. We had a 2 megawatt gas-fired heat exchanger in the system that was currently operating. We replaced that with a POWERSAFE medium voltage electric heating system, included the vessel, the heater, and the controller to install to replace that gas-fired heat exchanger. The overall value proposition obviously was lower total cost, more precise process control, reliability in the system, and obviously less carbon emissions. The next one we'll go through is a refinery upgrade in France. This was a hot oil system. Again, they were using a steam-generated type of heat exchanger powered by fossil fuel. In this particular case, again, the case for change was based on reducing those overall emissions of CO2 and the usage of natural gas within the system. That particular usage of natural gas represented around 1% of the refinery's CO2 emissions and about 19% of their CO2 reduction plans moving forward. Again, we were able to replace that with a medium voltage electric heater and provide our technical capability along with the medium voltage solution to ensure that they were meeting their objectives. At this point, I'll hand it back to Ken, who will take us into Q&A.